Sometimes integral can be discussed in a differential equation form. I mean, for example, let's consider the following integral: 6x squared minus 4x dx. So the result of this integral is a function of the x. So let's denote by the y. So y equals this integral. Equivalently, this integral or result of this integral and the solution of this equation, derivative of the y with respect to x equals 6x squared minus 4x, are the same thing. I mean, for example, here y equals 6x cubed over 3 minus 4x squared over 2 plus constant term c. If you replace this y in this equation, you can observe derivative of this is 2x cubed minus 2x squared plus c. The derivative of the y with respect to x equals 2 times 3 times x squared minus 2 times x plus 0, so which is 6x squared minus 4x. So the solution of this equation, this is called a differential equation, is the same thing of this integral. In general, an equation is a differential equation if it involves an unknown function and one or more of its derivatives. Let's give some examples for the differential equations. For example, dy over dx equals k times y. This is also differential equations. Let's write another example. Second derivative of the y minus x times y prime plus x squared over x squared equals 5. This is differential equation. Or dy over dx equals 2xy, etc. We will not discuss the solution of the differential equations in this course, but for some special case, by using integral, we can solve. Okay, so I will not analyze systematically solution of the differential equation in this course. Here, there is a first derivative of the y, and also in the last equation there is a first derivative of the y. So because of this reason, the first equation and the third equations are called first order differential equations. Here we have a second derivative of the y and the first derivative also, but the highest derivative is second derivative. So this equation is called a second order differential equation because it involves a second derivative but no higher derivatives. In this section, we emphasize a new special first order differential equations that have immediate and significant applications. We start by looking at some first order equations geometrically in terms of slope fields. We then consider continuous compounded interest as modeled by a first order differential equation. from this treatment, first order differential equation as a modeling component continuous interest, we can generalize our approach to a wide variety of the other type of the growth phenomena in this section. Differential equations and slope field. Okay, let's focus on this idea. Differential equation and slope fields. We introduced the concept of the slope field through an example. Consider the first order differential equation. dy over dx equals 0.2 y. So a function f is a solution of this equation, okay, which is y equals f of x. So let y equals f of x be solution. The geometric interpretation of this equation give us the slope of a solution curve that passes through the point x, point y. For example, if y equals f of x is a solution of this equation that passes through the point 0, 2, then the slope of f at the point 0, 2 can be calculated easily from the differential equation. I mean, for example here, our point 0, 2, this point, okay, we consider the solution which is passed through this point, y equals f of x. So dy over dx at the point 0, 2, here y is 2, so this is 0.2 times y is 2, so this is 0, 4. So this means the slope of the y equals f of x function, the slope of the f of x is 0.4. In other words, f prime at the point 0 is 0.4. Okay, so here the tangent line has the 0.4. So this slope of this tangent line is 0.4. I don't know what's the function, but slope of the f of x here 0.4. Okay, this is the slope. Red line is the slope of that line. So this is y equals f of x line. So at another point, for example, minus 3, 1. Minus 3, 1. So this point is minus 3, 1. So what is the slope at that point? Derivative of the y with respect to x at the point minus 3, 1. Y is 1. So 0.2 times 1. This is 0.2. So again slope is positive, but 0.2 it is a bit different than from the previous one. So the slope like this one. At another point you can calculate slope like this one, etc. So all of these line segments slopes show us the slope field of this differential equation. For example, let's try to sketch what is the equation 0.2y. So dy over dx equals 0.2y. So this graph, this slope field graph, gives us a lot of information. Okay, at the point 0.2 we have already sketched 0.4 like this one. at the point minus 3,1, which is 0.2, slope like this one. Okay, actually, as you see, this is not depends on the x. So when y equals 1, always slope is 0.2. So always slope is the same when x equals 1. So we have the same tangent line, okay, this slopes. When x equals y equals 2, so always slope as 0.4, like this one, like this one, like this one. So slopes are the same. For y equals 3, slope a bit sharper, etc. So like that one, 0.6, 0.6, 0.6, etc. But on the y equals 3 line, which is the same, always solution of the differential equation has the same slope. Okay, so for example, when y equals 0, this is the derivative is 0. So this is tangent line. This is the 0 line. For y equals 0, our tangent are parallel to the x-axis. For y negative value minus 1, slope are negative. So we have the some negative minus 0.2 line. Like this one. Like this one. Minus all length of the all tangent line are the same and slope are the same. When y equals minus 2, the slope a bit sharper like that one. Okay, this is the another slope. So this line segments is the slope field of the differential equation. The solution of this differential equation is y equals c times e to power 0.2x. Okay, you can solve. I will explain maybe when we need. But now you can verify easily whether this is solution or not. Derivative of y with respect to x equals c times derivative of e to power 0.2x is itself times derivative of the 0.2x 0.2. So now this is y. So this is 0.2 times y. So derivative of y with respect to x equals 0.2 times y. So this means this is the solution of our differential equation. So what is the graph of this differential equation? Easily we can sketch one of them, for example, for c equals 1, for c equals 1, this is the y equals e to power 0.2x graph. For the c equals 2, we can sketch another graph. For c equals 2, we have this graph, for example. 2 times e to power 0.2x. So clearly we can show that this is tangent line of to this curve, this is tangent line of to this curve at that point, etc. And also, for example, this is tangent line of to that curve. You can show that any tangent lines on the curve. So the graph of the red line segments show us the graph of the slope field of the differential equation. Okay, so directly from here we can sketch this one, but to sketch the graph of the blue one we need the solution. Okay, if c is negative, our graph likes that one. For example, minus 1 case, for c equals minus 1 case, this is also solution. Okay, so y equals minus e to power 0.2x is the another solution. Let's focus on the economic area. This differential equation can be accurate for the continuous component interest formula. Okay, so we would again revisit this phenomena, continuous compound interest. Okay, this is revisit. Let P again, be the initial amount, principal, okay, of the money that deposited in an account. This is initial. And A be the amount in the account at any time, future value, okay, the amount in the account at any time. Instead of assuming that the money in the account earns a particular rate of the interest, suppose we say that the rate of the growth of the amount of the money in the account at any time t is proportional to the amount present at that time. So what that means, change of the amount at any time is proportional to the money in the account at any time. So derivative of the A, since dA over dt is the rate of the growth of the A with respect to t, is proportional with the A. Actually, Turkish people show that this proportion like this one. So we have some proportional constant. So this is, let's say this proportional constant is the R. So which equals R times A. And what we know that initial amount is P. So amount when t equals 0 equals P. So this is the initial price. Of course here A and P are bigger than 0. So this is differential equation. Actually, since we know the initial value, this is initial value problem. Okay, this is initial value, called as the initial value problem. How we can solve this differential equation? Actually, you know the solution, but step by step I will explain how you can solve this differential equation. From here, derivative of the A with respect to t equals 1 over A equals R. This is constant. So if we integrate both sides with respect to t, you will obtain dtr cancelled. So integral 1 over A dA equals integral R times dt. R is constant. So left hand side, integral of the 1 over A with respect to A is ln absolute value of the A. A is positive, so absolute value is not necessary. R, integral of the R is R times T plus constant term C. So this implies A equals e to power R times T plus C, and right hand side e to power R times T times e to power C. You can consider e to power C as a new variable C. So as a result, future value equals C times e to power R times T. But we know what is the C. Why we know? Because we know the initial value. So for t equals 0, A of 0 is P. So A then for t equals 0 equals C times e to power from here R times 0. E to power R times 0 is 1. But A of 0 means A when t equals 0. So this equals P. So this implies C equals P. As a result, A equals P times e to power RT is the solution of this differential equation, okay? This differential equation which satisfies this initial condition. So by that way, it is deleted. I don't know here. Okay, so by that way, we obtain this important formula, which is known as a continuous compounded formula, as you know. As you realize, this is the same continuous compoundedness formula obtained in section 4 in the previous term, where the principal P is invested at an annual nominal rate R compounded continuously for T years. In general, we can give the exponential growth law if for any quantity Q with respect to time change is proportional to the quantity and the initial value of the quantity is Q0. So from here we can say that the Q function equals Q0 times e to power R times T, where Q0 is an amount of Q at T equals 0. R is relative growth rate expressed as a decimal. T represents time and Q is the quantity at time T. At time T. The exponential growth law applies not only the money invested at interest compounded continuously, but also to many other type of the problems: population growth, reactive decay, the depletion of natural resources, and so on. Okay, but in general, in this course, of course, we will focus on the compounded continuously, interest compounded continuously.